dynamics. Okay, and we'll only focus on manipulators, though you can look at control of a mobile car when there is a model for the motors, or if you have an IC engine and so on. Okay, so what we've done is we've looked at the Euler-Lagrange equation, right, to derive the equations of the manipulator. So they look something like this. Okay, so this is what we got from Euler-Lagrange, where tau is the torque. So what we did in the class was we took these equations and we simplified it. What we did was to simplify this equation as AX equals B. And what that really is that AX is actually Q double dot equals B. Okay, so the acceleration, A times acceleration is B. Now, another way of writing this equation, and this is the way you can see it in, say, textbooks or in papers if you're reading them, is that they will actually expand out on these A and B matrices. A is actually what is known as a mass matrix, and then the B term involves what is known as the Coriolis force term. So that's typically abbreviated as C, CQ, Q dot times Q dot, still a minus sign, and minus G times Q. This is the gravitational part of the torque, and then there'll be a torque. So this is basically how the expression looks, just because in Matlab, when we're doing these computations, we don't really care how B and A looks. And that's why I just made it at AX equals B, and it was much simpler to do the math and go ahead. But for the controls part, we actually want to write it in a different way, as I've shown it here. So when we do the substitutions, we get MQ double dot equals minus CQ Q dot minus GQ plus tau. And so the equations of a manipulator are C, and my bad, this should actually be Q. It's only a function of state and not Q dot. MQ plus CQ Q dot times Q dot plus GQ equals tau. Okay, and I'll write down what these matrices are. So M is known as the mass and inertia matrix. All the inertia terms, mass terms will come there. C is the Coriolis acceleration, Coriolis and centripetal acceleration. Or you can call it torque. Torque is more relevant here because this term has units of torque. And then we have G, which is the gravitational torque. So for example, if the manipulator was stationary, there was no acceleration, then Q double dot would be 0. Q dot, which is the velocity, would be 0. And then you'll see that the torque is just equal to gravitational torque, right? Which makes sense. And then torque is tau. Okay, so what we are interested here is trying to control tau such that we get the manipulator to do things we care about. So for example, if you want the manipulator to go from point A to point B, when there are dynamics, then the question is, how do we control this torque, right? And so far, we've actually not looked at the case where we had control over the torque. We only looked at the case where we could directly command the joints to move the way we want. So for example, for the manipulator, when we drew the asteroid or circle, we just specified the values for theta, the angles. That's because we did not have the notion of torque. We just assumed that we could do whatever we wanted with theta. But when you control an actual physical system, you can only control a motor, and the motor is controlled through uh, some some uh, some proxy for torque. Sometimes it's torque, sometimes it's proxy for torque like current, and that current determines the joint angle Q, which then determines the motion. So you cannot directly control Q, but you can only do so through torque. And that's why it's important to know how to control torque. Okay, so looks like we are okay. Let me just start this, and we won't go much far. We just have a minute. I'm going to do the simplest case to motivate this. I'm going to assume that we're looking at a one-dimensional system, okay, 1D system, where the mass matrix will become a scalar. The C, will assume that it's a constant, like a damping force. And then we have, for the gravitational term, we'll just take a spring force equals tau. So this is basically damping. This is like a spring term. And then this is the mass. So effectively, this system is like a spring mass damper system. Okay. What I'll do next class, I'm out of time, is that I will show you how, what is the response of the system when there is no torque. And then I will show you how we can control the system to do what we want by controlling the torque appropriately. Okay, I'll stop. And so this is the last section of the course on control of manipulators, and I'm guessing it'll take me maybe 2 or 3 lectures to finish. Okay, so I'm starting off from where I left last time. We talked about control of manipulators. We've seen that the equations of motion can be written by using the Euler-Lagrange equations, which are written here. Okay. What that does is it gives me the equations in this form, right? Where x is the acceleration of the degrees of freedom, so joint angles, or um, it could be the distances if it's a prismatic joint. And it turns out that the A matrix is actually what is known as the mass matrix. It has mass terms, inertia terms, and also the angles. That's why there is a Q. The B, the right hand side, has the torque, the gravitational torque, and then the centrifugal acceleration terms. So this equation is actually rewritten as following. It's mass times q double dot plus c, which is the Coriolis centripetal acceleration terms, times q dot plus g times q equals tau, or torque. Okay, and this is what you will see if you happen to read papers on this topic of manipulators. That's the equation you'll see. Okay, now given this equation, we will now talk about how to control the system. To motivate this, what I'm going to do is I'm going to start off with the simplest example of a manipulator like system, where I'll replace the mass matrix with a constant term m, the damping with a constant damping term c, the gravitational torque, which is um function of q, as simply k times q. So think of it like a spring term, right? A spring has a spring constant times the displacement, and then the torque remains as it is. Okay, so with this, I'm going to motivate uh, some of the control techniques, and then we'll generalize this to a manipulator with n degrees of freedom. So here we're looking at a scalar term. So this won't be a mass matrix, but it'll be a mass term. Okay, so it's a one-dimensional equation. Okay, so what I'm going to do now is I'm going to start assuming, well, first let's see what happens if the torque is zero. That is, there's no external torque acting on the system. Okay, so if I put tau equals 0, then I get mq double dot plus cq dot plus kq equals 0. Okay, and now it's actually a spring mass damper system. So let's try to sort of write this in the form in which you might have seen this before. So I divide throughout by the mass, get this equation. And now, if you remember, this can be written as in terms of a damping constant times q dot plus omega n square q equals 0, where the damping constant eta is simply, or rather, if you compare the two, so let's compare 1 and 2, and we see that 2 eta omega n equals c divided by m, and omega n square is k divided by m. Okay, this is the traditional way in which a spring mass damper system is written, right? So what we can do now is we can actually solve for omega n. It's k divided by m. Square root of k divided by m, and we can sub this value inside here to get 2 eta square root k divided by m equals c. And so we can solve for eta as c divided by 2 square root m times k. Okay, so remember this. This is the natural frequency of the system, and this is the damping, what is also called the damping constant. Natural frequency. Okay, so given this, we can actually plot the response of the system for different values of damping constant. So we look at three cases. One is the damping constant is greater than 1, which implies that if you see the expression here, C damping is C divided by 2 square root m, so C equals 2 times eta square root m k. And so when I say eta is greater than 1, it really means C is greater than 2 square root km. Second case is the damping constant is equal to 1. So in this case, C equals 2 km, square root km. And then the third case is eta is less than 1, which is C is less than 2 square root km. So the first case, where the damping is greater than 1 is known as an over-damped system. So those who have done a course in vibrations should not see this as something new. This is probably something which is often comes in the course in dynamics involving vibrations, or even if you've done engineering dynamics before, you might have seen this. So what does it really mean to be over-damped, critically damped, and under-damped? Well, if you take the system and you perturb it, so you essentially Q is the response or the position. If you start off with a value which is not equal to 0, so let's start off, say here, this is Q0, and that Q0 is clearly not 0 because the 0 is up there. Then depending on the damping factor, eta, you will get different responses. So first, let's look at what happens when the system is over-damped. So when the system is over-damped, it'll go to 0, but it'll do so very slowly. If it's under-damped, then you'll see that it actually oscillates, something like this. This is under-damped. And then if it's critically damped, then it actually goes to 0. It looks very much like an over-damped system, but it goes to the Q equals 0 much quickly. Okay, so always we want a system to go to 0 as fast as possible. And if you make it under damped, then it'll have these oscillations which are undesirable. If you make it over damped, that will go to zero in one direction. That is, it will not go positive, negative, zero like the under damped does, but it will take ample time. The best you can do is actually ensure the system is critically or under damped. Sorry, this is incorrect. This is critically damped. This is the best you can do. So our goal in controlling a system is always try to get the system to be critically damped. Okay, and why is that so? That's because it goes to Q to 0 in the shortest time. Okay, which means that we want to ensure that the damping is equal to 1, or in other words, C equals two square root km. So we'll strive to get the system to be critically damped. Okay, now if you take a generic system and you perturb it and there is no torque, like the one I just wrote down the equation for, right? So this is a system where there is no torque, and you cannot quite control the system in terms of how you can affect the damping, because the damping is fixed. It's a property of C, which is a system parameter, and M, which is also a system parameter, of course, K. Okay. However, if I told you that the torque is not zero, then you can actually influence this damping ratio and also the natural frequency. And so the goal here is to use this torque, okay, which is set to zero here, but in general it is not zero for a general manipulator with a motor. So we will set this torque to get the system to do what we want to do in the next section. So we will use tau to make the system critically damped. Okay, so here's how we do it. Okay, so now I'll rewrite the same equation I wrote before, but keep the torque not equal to zero. So I have kim q double dot plus cq dot plus kq equals tau, where tau is something which I can set using the motors. Okay, now the simplest control I can think of is it's a what is known as a PD control, or a proportional derivative control. So something like this. There's a gain, or a proportional gain called Kp, which multiplies with Q, and then there is a derivative gain which multiplies with Q dot. And since it's sort of going to extract energy from the system, I need to put a negative sign. So what I'll do is I'll take this torque equation, put it in the system dynamics. So this is the system. Put 4 in 3, and I get mq double dot plus cq dot plus kq equals minus kpq minus kdq dot. And now I can rearrange terms. I can move the kp kd on the left side to get mq double dot plus c plus kd q dot plus k plus kp q equals 0. Okay, now what we realize is that the middle term has two parts: c, which is depends on the system dynamics, but there's kd, which we can choose to be whatever we want. Similarly, the term involving q, there is a k which is system dependent, but there's a kp which we can tune. So now what we can do is we can rewrite the equation in the form we wrote earlier: k plus kp q 0, And remember, we're trying to get this in this form, q double dot plus 2 eta omega n q dot plus square q equals 0. Okay, so what we said is for the system to be critically damped, we said that C equals 2 square root Km. Now, this C is basically the term involving Q dot. So I need to put this as C plus Kd, right? Equals 2 square root K. Here the K is K plus Kp. And then the mass mate is the same as M. So this is the condition for critically damped system. And the good news is that we can change it to the way we want because we have control over Kp and Kd. We can tune this. Okay, so if we can tune this the right way, then we can get the system to be critically damped. So what I'm going to do is, well, before we solve this, realize that this is one equation, but then there are two tunable parameters, and they are Kp and Kd, which means that you have more flexibility than you really need, right? You only need to choose one number, and the other number you can vary it. You can change it the way you want. So what I'll try to do now is solve this equation for Kp in terms of Kd. Okay, and for that we'll have to square both sides. So I get C plus Kd square equals 2. Sorry, 2 will become 4. K plus Kp times M. And then if I square this, I'll get something involving a quadratic equation in Kd. Okay, and I'm going to skip a step. I'm actually going to move this right-hand side to the left-hand side. So I'll have minus 4 K plus Kp times M equals 0. So what I have here is a quadratic equation in Kd, right? The solution to that quadratic equation is basically, if you remember, let me just put it down, next page. So let's, we copy this first. Okay, so that's for reference. The solution of a quadratic equation is Kd equals minus the linear term involving Kd, so that will be 2c, plus or minus square of this term, so 2c square minus 4 times the term which multiplies with Kd square. In this case, this is 1, and then times the constant term. So it's going to be c square minus 4k plus kpm divided by 2 times 1. Okay, how did I get this? Well, if there's an equation a prime x square plus b prime x plus c prime equals 0, then the solution to it is x equals minus b prime plus or minus square root b prime square minus 4ac divided by 2a prime. This is the solution of a quadratic equation, and that's precisely the formula I used in order to get the value for Kd, which is in this case x in this equation. Now, what I can do is I can actually cancel off the common 2. I can pull that 4, and 2c square becomes 4c, and I can get Kd equals minus c plus or minus c square minus c square. So here we have c square plus 4k plus kp times m, and then the c square cancels with the other c square. And so I have kd equals minus c plus or minus. I can also pull the 4 out, so it comes out here, and then I have k plus kp times m. Okay, so that's it. So there are two solutions, one of them with the positive sign, one of them with the negative sign. Now, for sure, you don't want to have a negative sign here, because if you have a negative c and negative of a term which is positive, then effectively kd is going to be negative. And a kd negative is, it's actually called positive feedback. It'll actually make the system go unstable. Think of it like having a viscous term, and the viscous term is not damping the system out, but actually pumping in energy. So we can discard the negative root. And so we have kd equals minus c plus 2k plus kp times m. Okay, so that's the formula. Now, what this means is this prescribes a formula on kd. Okay, kp is free. It's a free parameter. You can take kp to be whatever you want. However, this is telling you that kd should be minus c, which is a system constant, and then there's k and then m. Okay, so kd is prescribed, but kp is not. And so if you use this formula, you should be able to get the system to be critically damped, right? To make the system be critically damped. Okay, so what I'm going to do is, let me illustrate this with a Matlab example. What I'm going to do is I'm going to take c to be 1, m equals 1, c equals 1, k equals 10. And so my equation is q double dot plus cq dot, so it's q dot plus kq, so it's 10, q equals tau. Okay, so then I would have tau equals minus kp q minus kd q dot. And if you use this formula, we get, from this formula, we can get kd equals minus c, but c is 1, plus 2 square root k. So k is also, well, k is 10, plus kp times m is 1. So this is basically saying that as long as my kd is this particular formula, where kp is a free parameter, I should have the system critically damped. So what I'm going to do is set this particular gain kd, choose anything I want for kp, and then see what happens if I start the system with initial condition, which is, let's say, 0.5. So q at time t equals 0 is 0.5, and q dot, which is the velocity at time t equals 0, is 0. So I start the system at 0.5, and then if my calculations are all right, then I will see the system will damp out in a critical fashion, which means that it will go to 0 in the shortest possible time. This the code I wrote to illustrate this particular example. We have a mass matrix. The mass is 1, the damping is, the c is 1, and k is 10. Now, as I said, the kp is something we can choose. Let's choose it to be 1, and then kd comes from the formula I wrote down earlier for on paper, right? Okay, so what I've done here is I've used ODE4 to integrate. You could use ODE4.5, whatever you like, but essentially set up the initial condition q, velocity 0, and then I use ODE4, where the right-hand side is over here, which is basically the equations of motion. Here, I wrote a formula explicitly for q double dot, okay, which is again from the formula I wrote down on paper. Okay, so let's run this. And what I get is, here is position as a function of time. And you see that the position starts off with 0.5, but quickly, well, damps out in about 2 seconds, we have it close to 0. Okay, so you can see that it's not over damped, it's actually sorry, it's not under damped, so you don't see the oscillations, but it is also not over damped, because then you'll see the response is much slower. So what I'll do is I'm going to actually ramp up the gain kp and show you that this actually response time actually slows down, so or much the it gets to 0 much faster, so it's actually much faster response than what I had before. So let's change kp to, let's say, 10, and then rerun this, and then this is what I get. You can see it was earlier at 2, now it has become less than 2, maybe 1.8. Let's further ramp this up to 100, and then we see that it is now takes less than 1 second. And then if you can keep ramping up, you see that it's now 0 in less than 0.5 seconds. Okay, now some point this will break. For example, if I do 10,000, then it actually breaks down. So here is, but it's not, actually it does work for 10,000. Some point of time it breaks because my integration is accurate to only to so many decimal places, right? 10 raised to negative 3. So here it actually works. So it's pretty good response, like bang on target within less than, I don't know, it's very hard to see here, but in the few milliseconds, it actually gets to where it needs to be. I'm just trying to see if where I can break this. It actually still works. I'm still amazed that it still works. Some point of time, it should just blow up. Yeah, there it is. So now if I change it to, I don't know, 10 million, 1, 2, 3, 4, 5, 6. Yeah, it's 10 million. So if I do 10 million, then you see that you get 10 raised to 300. That's because this is beyond the tolerance of the integrations. This will not work. Okay. The other place where this will not work is when you have noise in the system. When there's noise, then if you keep increasing the gain, the noise will get amplified and drive the system to be unstable.